So here we have one of my favorite trig identities show that questions. It's a great question because it involves so many of the different identities that you need involved in this trigonometric aspect of the A-level maths course. I always start with this question at some point when I'm introducing this for students because it's got all the things that you need to practice in it. So what we've got, sine 3 theta is equivalent to 3 sine theta minus 4 sine cubed theta. So we're going from a triple angle down to single angles. So before we go through the proof, there's just a few principles we're going to need to use. First one is probably the easiest one you might ever see in an A-level maths video. 2 plus 1 equals 3, of course. You might think that's the most obvious fact, but we're going to use that. We're going to break down this 3 theta. We can split it up using the fact that 2 plus 1 equals 3. We're also going to use this fantastic identity that sine squared theta plus cos squared theta equals 1. So this is one of the most important ones. That comes from this lovely right angle triangle with hypotenuse 1, angle theta here. So your opposite side, the vertical component, is sine theta, and the adjacent side here is cos theta. Now this comes from the unit circle. This is where sine and cos come from. From that, you can see that because of Pythagoras' theorem, that the sum of the squares of the shorter sides is equal to the square of the hypotenuse. So sine squared theta plus cos squared theta is 1. We are also going to use the compound angle. So the compound angle is formulae are when we're trying to expand. We've got the addition of angles within the function. So if we've got sine of a plus b like this, we need a way of separating this out into separate bits. So the formula tells us that sine open bracket a plus b is equal to sine a cos b plus sine of b cos a. There's a nice geometric proof of this which I'll show you in another video. We also are going to need what's called the double angle identities. So we'll start off with sine 2 theta. Now sine 2 theta, we can actually use what we've got above. So if I was to replace theta with a and b, then that would mean that all the way through this formula we just got theta. So the idea, theta plus theta is 2 theta. So what we've got above, we'd have sine theta cos theta plus sine theta cos theta, which would give us 2 sine theta cos theta. Now the double angle for this one, turn into equivalence, there's only one real option that generally we use for this, so that's quite nice. For cos 2 theta, there's actually a few options. Now I'm not going to go through prove these, but the first one we tend to derive is that. Using the identity on the previous slide, where we have sine squared plus cos squared equals 1, we can actually do some swaps. So we can say that 1 minus cos squared theta is equal to sine squared theta, and also the same with the other way around. So we can actually change this. If we change cos squared to 1 minus sine squared, we can actually get this one, and we can actually get this as well. So if we swap sine squared for 1 minus cos squared, we get this. So when you're doing manipulation with these trig identities, the sine one is really nice because there's only one option you're ever going to choose, and the cos one is nice because it's versatile, so you've got these different options. We can also do a nice little factorization of this. I'm probably going into a bit too much detail, but using difference of 2 squares. Sometimes it's useful to use that as well. But today, so what we've got is we've got 2 plus 1 is 3. We've got this identity, we've got a double angle, we've got a compound. So let's tackle the question. So the left-hand side, we could say is equivalent to sine of 2 theta plus theta, because 3 theta is 2 theta plus theta. Now we can use our compound angle. So we've got if we call this A and we call this B, and using what we had previously, we can say that this is equivalent to sine 2 theta multiplied by cos theta plus sine of theta multiplied by cos 2 theta. Now we can use the double angles. Now, as we said before, there's only one option for sine 2 theta, so that would be 2 sine theta cos theta. So replace that with that, and we're going to multiply that by cos theta. And then you've got options for what we want to use to replace this cos 2 theta. Now, previously we had those three options. Now, the one that we want to choose is going to be the one that allows everything to be in terms of sine thetas, because the final answer we're looking for 3 sine theta minus 4 sine cubed theta. That's all sine theta. So if we choose the 1 minus 2 sine squared theta, that's the smart option. And so now we've replaced our double angles in with their single angle versions. So we multiply out cos times cos is cos squared, so we get 2 sine theta multiplied by cos squared theta. And we get plus sine theta and minus 2 sine cubed theta. Okay, so next we're getting closer. So we've got 2 sine cubed theta here, which is looking similar to the sine cubed up above. We've just got this cos squared, which is we need to eliminate. So what we can do is use that first identity we had. Cos squared theta is 1 minus sine squared theta. So we've got 2 sine theta, 1 minus sine squared theta, plus sine theta minus 2 sine cubed theta. Multiply out our brackets, so we get 2 sine theta, and then we've got 2 times sine theta times minus sine squared theta, so we're going to get minus 2 sine cubed theta. We've got this bit on the end, and so nicely all comes together. So we've got 3 sine theta minus 4 sine cubed theta, which is what you were trying to get to. So that is your right hand side. So we've finished our proof. So the reason I like this as a question, it's a really good one to practice, is because you've used your compound angle, you used your double angles, you've had to choose both options, you've had to use this identity here. So I'd say this is a nice one to practice. So moving on from this, what would be a good thing to do is to show that cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta. Tidy up this little square. That's a nice example to try. The other thing is there's another way of doing this. So there's a theorem called de Moivre's theorem. Any further mathematicians, if you're learning about complex numbers, it's another way of doing it. It's actually, you might argue, is a little bit quicker. So that's another method I will show you in another video. So hopefully that was clear. Have a go at doing cos 3 theta, and if you want to research, look into de Moivre's theorem, and that should keep you busy. Enjoy!